So the first thing on here is this little sort of motivation for the chain rule, which is to say, let's say that we got these three little wheels. So I'll sketch them here. So we've got three wheels of descending sizes. And of course my sketch is really terrible. And let's say that the radii are 15, 10, and 5, okay? So the question I want to answer is, and we can do this sort of either way, if I rotate wheel A exactly once round, how many times does wheel C rotate? Well, not exactly obvious from that, but how would we sort of figure that out? I mean, what's an easier problem here? What about if we just had wheels, say, A and B? Well, or even, because this will make it really easy, B and C. Every time wheel B rotates, how many times does wheel C rotate? Twice, right? And why is it twice? Because, yeah, half the radius, or twice the radius, depending on which, side you're thinking about. Okay, and what really are we, what quantity is sort of important? The radius is important, yes, but then what do we get from that? Yeah, so the circumference of wheel B is twice circumference of wheel A, so if wheel B rotates once, and wheel C is sort of, tied to it, like really imagine these as gears so that they're locked together. It's a lot harder to draw gears in Illustrator than, so I just did wheels. Okay. Basically what you're looking at is the ratio of the radii, right? Okay, so the rate at which A turns, so if I want to know how many times does B turn for each turn of A, right? Well, what's the ratio of A to B? 15 to 10, or, yeah, A over B symbolically, okay? And so it'd be 15 over 10, okay? All right, and how many times does C rotate given a rotation of B? 2, right? And we got that by 10 over 5. All right, and so if I want to ask how many times does C rotate for each rotation of A, what I'm looking for is the ratio of A to C, or C to A, depending on, we can always flip everything upside down, okay? All right, well, this is sort of the trick. I'm going to say, all right, well, A to C is the same as A to B times B to C. And I know each of those quantities already, right? 15 to 10 and 10 to 5. And notice that in a sense the 10s cancel, right? And so what do we get? 3 to 1. Okay, does that kind of make sense? Yeah, just intuitively? All right, so that's sort of this idea of having a dude in the middle, okay, gear B, is sort of the motivation for this thing called the chain rule, okay? Okay, so, I mean, because we're not here to be in the business of talking about wheels and gears all day, but that does serve as sort of a handy motivation for the problem. Okay, so from a calculus standpoint, here's what we're going to do. Okay, let's say that I've got two functions. F of u is u squared, and u of x is 2x plus 5. Okay, so I'm going to think of, in the first function, I'm thinking of u as a variable. In the second function, I'm thinking of u as the actual function, but it's the same u. I'm just thinking about it in two different ways. Okay, so like with the gears, if I asked, what's the rate at which f changes based on u changing, that's code for what's the derivative of f, where u is the variable, right? Or symbolically, df over du. Well, what is df du given this thing? 2u. Okay, that's easy. And then, similarly here, u is a function of x, and so I could ask, well, what's du dx? And in this case, what would we get? 2, okay, because the function happened to be linear. Okay, and so then if what I wanted to answer is the following question, what is df dx? Well, could we kind of think of this like we did with the wheels? That we've got f, u, and x is the wheel on the far right, and u is the wheel in the middle, and f is the wheel on the left. Well, if we did sort of by analogy, we could say, oh, well, maybe it's something like this. And it is. Okay? So this is one way of writing the chain rule in Leibniz notation. Okay, so remember, what's the difference between Leibniz notation and Newton's style notation? Yeah, Newton's the primes. Okay, and we will write the chain rule in prime notation in a minute, but I started with Leibniz notation because doesn't this look a whole lot like what we just did with the gears? Okay, now, to be clear, df du and du dx and all of those things, do they look like fractions? Yeah, I'm writing them with a thing over another thing with a bar in the middle. That sure as hell looks like a fraction, but they're not really fractions. Okay, so and believe me, the philosophy of sort of what the heck is the thing that we're writing down has been bothering mathematicians, well, basically since Leibniz. So, yeah, okay, but it's sort of like if you pretended for a moment that they were fractions, you'd be like, oh, well, the du's cancel, no problem. Well, they don't really cancel in the sense of fractions, but this is sort of one of the benefits, I think, of Leibniz notation is that even though they don't really cancel, they sort of do. Okay, I know that's not probably the most satisfying thing to hear a mathematician say at 8 in the morning, but yeah, okay, so good. All right, so what did we get for df du and du dx? Those two things, we'd have 2u times 2 or 4u. All right, now, is that a satisfying answer? I mean, it's an answer, but would I be completely satisfied with it? Why not, Thomas? Yeah, exactly, because the question I'm trying to answer is a relationship between f and x, not f and u or u and x. Okay, so I would like this to be in terms of x because I'm looking for df dx. Okay, now fortunately, as Thomas said, what is u? It's 2x plus 5, right? We know that, so we can just substitute that in. And get 8x plus 20. Okay, no big deal there, right? Good? And we could sort of double check that this makes sense because what about if instead I go back and do this from the beginning and say, that's really the function in terms of x, right? And in this case, because it's 2x plus 5 squared is pretty easy, right? Can I just FOIL everything out and just do it the long way? Right, that's sort of your idiot check to make sure that everything works out right. So let's just FOIL it and do the derivative that way. So what are we going to get? We get 4x squared plus 20x plus 25, right? And then if I took the derivative of that, I do in fact get 8x plus 20. Okay, so it worked. All right, does that kind of make sense? Yeah? Now, the reason that we want to do this, though, is, or have this sort of alternative method, is because what about if this was 2x plus 5 to the 1,000? I mean, yeah, you could FOIL it out, but you'd be at it for a little while. Okay, and so clearly, like, another method is necessary. Okay, so flip over to the next side, okay? And so here what we want to do is basically say, to write everything in, there are two different notation systems, right? So we've got Newton style and we've got Leibniz style. Now, if you look on the sheet there on the right, that's got the Leibniz style, which is what we've already done, right? So okay, so let's say so let's just rewrite it. So Leibniz, right? So, and for both of these, actually, let's just remind ourselves of what the function was. So we had f of u was u squared, u of x was 2x plus 5. Okay, so Leibniz style is to say df dx is df du times du dx. And then what was df du? It's 2u times 2, and then plug in. Okay? Okay, so that's what we already did. All right, Newton's style would be written a little bit differently. Same functions, and in fact, we'll get the same answer. Okay? So the Newton style way of writing the chain rule is to say, if you have f of u of x prime, and you want to take its derivative, okay? So f of u of x, what really are we doing here? This is function composition, right? Okay? So what is the derivative of function composition? It's the derivative of the outer one with the inner one then plugged in times the derivative of the inner one. Okay, so let's sort of think about why these two things are equivalent. They sure look different. Yeah. Okay, so the u prime of x part, what is that the same as in the Leibniz version? Du dx, okay? df du is the f prime thing with u plugged in, right? So that was what we had to do at the very end, right? We said, well, we want our answer to be in terms of x, so if I see a u, I'll replace it with whatever u was, okay? Okay, which way do you like better? Or which style of writing do you like better? Newton, okay. Leibniz, okay. There is an advantage to Leibniz style that's not so much apparent here, but in multivariable calculus, where you've got a lot more variables flying around, it actually can make the chain rule a little easier to write down. But that's for another day. Okay, so we've got here 4 functions. Let me just write them down. so take a moment and let's work through these. Oh, I forgot to give that a name, but whatever. Okay, so the first thing to identify here is, okay, so this is one thing that's different about these four versus the one we started with. In the one that we started with, I told you what F and what U were. In this case, you've got to choose U. Now, it probably is going to be pretty obvious, right? So for all of these, what's the function F in terms of U, and what's U in terms of X? Okay, so decide that, and then do what we did for the previous example for all four of these, and write it both Leibniz style and Newton style, right? Because I want you to be comfortable with both. Okay, so does that kind of make sense? Yeah? All right, so take a few minutes and do that. And whilst you're doing that, I'm going to try not to break my neck. Supposed to just slide, but I'm gonna go grab Jill and show her the issue. Hey Jill, borrow you for a second. I need you to follow up with cancer about something. Well, sort of. They work, except
they're getting an electrician in.
oh, okay.
Huh.
Great spot for it, huh?
I'll see if maybe they can move that.
Well, I tried, but they don't seem to want to. Yeah, maybe they're supposed to, I thought, but I just must not be giving it enough grease. But yeah, it's kind of tacky.
Yeah, I'll mention that when I talk to them.
Okay, cool. Thanks. Because if they could just slide it down to here,
Yeah.
right, and then angle it, or whatever, but. All right, so what do we get? Number 2 is basically the same as the one we did, right? What's the difference, though? Well, much bigger exponent, right? All right, but what'd you guys get? 1832 times 2x plus 5 times 2, right? Oh, yeah, duh. 1832 times 2x plus 5 to the 1831 times 2. Yeah, this is why coffee was invented. There was a mathematician, Paul Erdős, who once said that a mathematician is merely a machine for turning coffee into theorems. Coffee goes in, theorems come out, occasionally bathrooms come out, but yeah. All right, so yeah. So let's do well, let's just write out number 4, okay? If I go ahead and write it as f of u would be e to the u, and u of t would be sine t. Okay, do you guys agree of that sort of decomposition? Okay, and so if we then write this out Leibniz style, what's df dx is that's what we're interested in. It's df du what's the derivative of e to the u? E to the u itself. What's the derivative of sine t? Okay. And then, what was u? Sine, so I'm just going to replace it. Okay? All right, so does that kind of make sense? Now, here's the way, like, the big boy version of this is to not actually write out this, okay? The idea is after some practice, you can go directly to the answer, okay? And here's sort of how I think about that. So let's just say, if I want the derivative of e to the sine t, well, I'm going to think of this as e to some stuff. What's the derivative of e to some stuff? E to the stuff times the derivative of the stuff. Okay? Now, what's the derivative of the stuff? Cos t. Okay, and that's pretty much it. Okay, so does that kind of make sense? Now, where this gets nasty is where the functions are worse. So let us turn our gaze to the next page for some stuff that is spicier. Okay, so the next one is kind of mango habanero, right? And then the one after that is the blazon. Not really, but huh?
Somebody likes beat-ups.
Yeah. Well, if I'm going to talk about them being spicy, right? What's the uniform scale of spiciness? Beat-up's wing spice level seems like a pretty. I mean, it's either that or I start writing these in terms of Scoville units. Yeah, ghost pepper. Well, they use ghost peppers and Carolina Reapers and stuff like that in the blazon sauce. They at one point had, this is before they remade their blazon, they had ghost pepper sauce. You know how they do like special sauces periodically? It was so spicy, I started hallucinating. Like, not like LSD acid trip, like I'm at Woodstock kind of hallucinating, but, or like Fear and Loathing in Las Vegas. It wasn't Fear and Loathing in Buffalo Wild Wings, but it was definitely a slightly altered state of consciousness. Oops. Yeah, it was an interesting experience, shall we say. So, no, actually, I did it a second time. All right, so the first one, all right, so let's say we've got sine of e to the 2x plus tangent of 3x. Okay, what makes this spicy is that it's not just sine of something. It's something where each of the things we're going to have to do the chain rule. Okay, so what's the derivative? So let me call this f of x. What's the derivative of sine of something? Cosine of the something times the derivative of the something. Okay, so I'm going to write it this way. Okay, now I guess my other sort of rule of thumb is don't try and do it all at once until you're got some practice in. Okay, so what I did there was I wrote the first step. what's the chain rule say? The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. Now, I'm not finished. I still need to know what's the derivative of the stuff. So I just wrote myself the instruction to do it, and I'll do that part on the next step. Okay? To make sure I don't botch this. Okay, so what is the derivative of e to the 2x? Yeah, okay, so how did you get that? It's what's the derivative of e to the stuff? E to the stuff times the derivative of the stuff. Okay, and in this case, the derivative of the stuff was just 2 because the stuff was linear. Okay, good. All right, so that's the first part. What about tan of 3x? Well, what's derivative of tangent? Yeah, secant squared. So we have secant squared of 3x times 3 from the chain rule. Okay? And could we simplify that? Not really, so I just leave it as so. Okay, does that kind of make sense? Yeah, this can get a little messy. Functions are quite complicated, but yeah. Now, remember what I said about the shortcuts back when we were doing the limit definition? Like, be careful what you wish for, because you just might get it. Well, guess what? You guys just got it. Right, the chain rule's the messy one. Okay, so there we go. You just got to be careful with order, and in a sense, we're kind of, I guess another sort of way to think about this one is we sort of worked from the outside in, okay? Because, like, you could argue that this one we actually have triple function composition instead of just, double function composition instead of just a single function composition, right? Yeah, just don't try and do it all at once, I guess. Okay, does that make sense? Yeah? All right, so let's do number 2 here. Was g of x was sine of log of tangent of e to the x. Okay, so we got some ghost peppers in here. All right, so what do we got to do? What's the derivative of sine of some stuff? Cosine of the stuff. Times the derivative of the stuff. Okay. Now we just got to keep going, right? So what's the derivative of natural log of some stuff? 1 over the stuff times the derivative of the stuff. So most of the work here is actually just copying things down. All right, what's the derivative of tangent of some stuff? Secant squared of the stuff times the derivative of the stuff. Okay, and then at the last step, what's the derivative of e to the x? No more stuff or chain rule involved, right? So the chain terminates. 3. And that's the best we can do. Okay. All right, so it gets kind of nasty, right, or could. I mean, to be fair, this function was sort of contrived to be nasty, just for the sake of illustration. Like, there's no reason why we would ever actually care about that function, but yeah. Okay, so does that kind of make sense? Question, preguntas, fragen? Nine? All right, excellent. Okay, so let me just kind of, oh, here, I'll leave that up for a second, sorry. Let's kind of think about what you guys did on Monday, right? So what was one of the things that you guys talked about with Dr. Gates on Monday? Think about the Burt Reynolds problem, the hat, okay? So what was sort of the issue there? What was going on with that problem? So Burt Reynolds was driving, and remind me of the rest of the story. There's an unusually large hat in the roadway, and he slams on his brakes, and then what? Yeah, so the question was, yeah, what was his rate at which he slowed down? What was his acceleration? Okay, so what was tough about that problem is that you needed to know if we suppose that he slows down with a constant acceleration, what's the velocity given that? Okay, well, that's a different question that we've answered a lot of. What we've answered questions are, given a function, what's the rate at which it changes? Right? We haven't done a whole lot of, given a rate at which something changes, what's the function that it could have come from? Okay, so what's the difference there? What's the magic word here? Well, the derivative would be if I gave you a function and I said, what rate is it changing at? What's the going the other direction called? Did he use this word with you guys? Antiderivative? Okay, so what does antiderivative mean? It's basically, let's imagine reversing the derivative process. Okay, so if I tell you the function is x squared, what's the derivative of that? 2x, okay, easy, right? Now, let's say, find me a function whose derivative is 2x. X squared certainly does the job, right? We're not morons, we just said that one. But are there others? Yes. And what do they all look like? Yeah, x squared plus any number, right? Because what would the derivative of the number part be? 0, okay? So, okay, so that's what we call, when you sort of mentally reverse this process, what you're doing is anti-differentiating. Okay, so here's the formal definition. Okay, so we say that a function big F is an antiderivative of little f if when you take the derivative of big F, you get little f back. Okay, so this would be like what we just did. If I said, find me a function whose derivative is 2x, and you answered x squared, is it true that x squared's derivative is 2x? Bueller. Is x squared's derivative 2x? Yes. Okay, good. Is that the only answer, though? What would be another answer? X squared, plus 4. Plus any other constant, okay? Because what's the derivative of the constant? 0, so we don't have to worry about it. Okay. This is why I use the word "an" antiderivative there. Because, as we discussed, there could be more than one answer. Now, that said, is it really, like, the x squared and x squared plus 4, are those really all that different? I mean, what's a plus 4 amongst friends, right? Right, it's just a constant. Okay, so anyway, so I claim here's what I want to know. I've got this function fatty f. Is it an antiderivative of that other thing? Okay. If it is, what do I need to do to determine if it is or isn't? Yeah, take its derivative. And what should I get when all's said and done, if it is? Yeah, I should get the little f x over the square root thing. If I get something other than that, and I'm pretty sure I didn't mess up any of the steps along the way, then it's not an antiderivative. Okay? Does that make sense? All right, so let's take the derivative of fatty f here. What is the first thing I've got to do, though, so that I can take the derivative? Yeah, okay, I need to rewrite the square root as an exponent. And what is said exponent, pray tell? Okay, so remember that square roots can be written as fractional exponents. And that's good because now our derivative rules apply. Okay, so Mr. Amore, what are we going to write here? F prime of, oops. Let's try that again. F prime of x equals, okay, okay, times 2x. Okay, why is it just 2x that I multiplied by there? What's the insides here? And the derivative of that is 2x. Okay, that's simple enough that I can just do it in one step. If it were more complicated, like in the last one, then write out an extra step just so that you don't screw it up. Okay, but in this case, that was pretty straightforward. And then let's tidy things up a little bit. What happens to the 2's? Okay, and what does a negative exponent mean? That thing, but in the denominator. Okay, and so I could rewrite this as that, okay, which was the given quantity. So is this an antiderivative of the other thing? Yes, it is. Okay. Right. So you, the Burt Reynolds problem, right? One of the things that you had to do there was to say, okay, let's suppose that there's a constant rate of acceleration, and I don't know what it is, so let me just call it c for constant. And then you had to say, okay, well then what would the velocity be that would give me that acceleration? So you were having to undo the derivative process. Does that kind of make sense? Yeah. Now, in the case of the Burt Reynolds problem, constant acceleration means linear function for velocity means quadratic function for position. And that kind of makes sense, right? Because think about, like, if I throw a ball, or any other object for that matter, right? If I throw this DisplayPort adapter at Mr. Amore, right, what's the trajectory it's going to take? It's going to be parabolic. Right? You guys have been throwing things for many years of your lives. So, yeah, it makes sense. Okay, and what's the acceleration in this case? once it leaves my hand? Huh? Not 0. Well, I'll give you a hint. Force is mass times acceleration, right? What's the force that's being applied to it once it leaves my hand and is in flight? Gravity, right? So the acceleration there is constant downwards at negative 9.8 meters per second squared. Interestingly enough, this is fun trivia. I don't remember the exact number off the top of my head, but many, many years ago, like maybe 100-ish years ago, somebody, I don't remember, was doing a gravitational study, and so what they wanted to do was determine what is the local gravitational constant at various places on Earth. And they did it for Crawfordsville, basically right out front of the Caleb Mills house. Okay, so we have the official gravitational acceleration. It's 9.81, and then there's a bunch more digits for campus, basically, which is just kind of cool to have it to that ridiculous degree of accuracy. Oh, anyway. Okay, so let's look at the next one here. Okay, so here, do I know the function? Do I know what f of x actually equals? No. I do know that what f prime is and what f of pi halves is. Okay, so would this allow me to find the equation of a tangent line? Okay, at a point, but which point is it got to be, given what I have? X equals pi over 2 is the only point that I know anything about the function. So if I don't use that point, we're sort of donezo. Okay, so tangent line, what I'm going to do is I'm going to write it in this form. Okay, mx plus b. That's ultimately the form I want to get it in. I won't start there, though. What's the more convenient way to write a tangent line? Okay, starting in point-slope form. Okay, so what gives us the coordinates of the point? Well, what are the coordinates of the point that I'm interested in here? What's the x coordinate? Pi over 2, and what's the y coordinate? 17. Great, and those numbers are just made up, right? Now, what's the slope going to be given by? The derivative. Now, we know the derivative. But we just need to plug pi halves into it. Okay, so here's where what is cosine of pi halves? 0. Okay, so what does that make the exponent? 0. And so the slope turns out, in this case, to just be 1. Oh, God, I'm a moron. Thank you. Yeah, e times 2, so it's 2e to the 0, which is 2. Okay, there we go. Well, you know what? I'm out. You just teach class from now on. How about that? Okay, so 2, not 1. We're cool? Yeah? Okay, so there's the slope. We know the point. So what's the equation? Y minus 17 is 2 times x minus pi halves. And if I rearrange this, okay, then I've got it in mx plus b form. Okay, so I'm going to think of this as being a new function which I'll call L. okay? L of x. L for line, basically. Okay, so does that make sense? Right? And that part we've done several times, right? Just cooking up the equation of a tangent line. Okay, now here's the fun question. Well, this is going to be hard to answer. Okay? We want to know, is L of 2 bigger or smaller than F of 2? One way to answer this would be, well, let's just compute F of 2. But can we? No, we can't. Okay? We can't compute F of 2 because we don't have a function F of x. We don't have the formula for it. Okay, well, that's good. All right, so what we're going to have to do to answer this question, let me draw sort of a picture here. All right, if I've got some function doing something like that, right, and I pick a point, and let's say that this is pi halves. Well, what is pi halves numerically, roughly? Yeah, 1.57, blah, blah, blah. Okay, so 1.6-ish. 2 is a little bit bigger than that, but not much. Okay? All right, so here in this sketch that I've made, let's say that the squiggle is F and the straight line is L. Okay? In this particular sketch, does it look like F of 2 is going to be bigger than L of 2? Yeah, okay, because the function curves upwards rather than remaining straight. I could have drawn it so that it curved downwards instead. Yes? Okay, so what is this code for if I'm asking, is it curving upwards or downwards? Huh? It's concavity. Another way to say that, though, is the slope of this thing is given by the derivative. I want to know how the slopes are themselves changing. Okay? Because what does it mean to be curving upwards? It means that your slopes are getting bigger. What does it mean to be curving downwards? It means your slopes are getting smaller. Okay? So what do I need to know here? I need to know what the derivative of f prime is. Does that make sense? Okay, well, what was f prime? It was 2e to the x cos x, right? Okay, so we know that f prime of x was 2e to the x cosine of x. Okay, f prime, not the original function. But could I take the derivative of f prime? Okay, yes. And how am I going to do that? Well, this is chain rule, right? So what's the derivative? 2e to some stuff times the derivative of the stuff. And how, Mr. Fisher, am I going to take the derivative of x cosine x? Don't give me the answer. Just what rule am I going to use, and then we'll worry about the answer. Not quite. Help him out, Mr. Gaines. Not quite. Correct first letter. Product rule, because it's a product of two functions. Right? All right. What is the product rule? Oops. So what's the product rule say? What do I need to write down? First thing times the derivative of the second thing. And what, pray tell, is the derivative of cosine? Thank you. Plus the second thing times the derivative of the first thing. Okay, so we agree with that? All right, so what I would then want to do is I would want to think about what value does this thing take on if we're, say, between pi halves and 2. Is this thing positive? Is it negative? Does it change sign? What's going on? Well, let's just plug in pi halves first off, just to see what happens there. Okay, so what are we going to get? Well, what's the e to the stuff part going to be? 2, because we'll get 2 times e to the 0. Then what about all this other stuff? So if I plug all this mess in, what am I going to get here? I'll have pi halves times, what's sine of pi halves? 1, good. Okay, so I just get minus pi halves. And what's cosine of pi halves? 0. Okay, so what do I get here? I get negative pi. Okay, whatever. I got a number. But the fact that this number is negative, so what should I expect? Is the function doing sort of this number, or is it doing sort of that number? It's doing this number. So who would I expect to be bigger, the function or the line? The line, because the function's going downwards. Okay, does that kind of make sense? Yeah? All right. Maybe we'll start and just kind of refresh on this one at the beginning next time. Yeah, okay, well, we actually got through the whole sheet basically today. Fantastic weekend, and just by way of reminder, what's happening Friday next week? Yes, your next celebration of learning. So, yeah. And you probably noticed that Canvas has sort of hit like there's nothing more there, because I've got a bunch of buttons to click and stuff after class to publish the next sort of chunk worth of assignments. So just be on the lookout for that. So, all right, see you guys on Monday.